This is Jim Hendershot. I'm presenting now lecture number 20. This is part one of two lectures on the design of rotors for asynchronous induction machines. The majority of AC induction machines used around the world for the past 100 years are fitted with aluminum die-cast squirrel cage rotors. Since that is the case, one might assume that these rotor designs are a trivial matter in the big scheme of things of using induction motors with inverters for variable speed and high performance applications. But that's not really the case. We have to point out that the shape of the bars in those motors was not a trivial matter. They were developed over many years as the torque and performance requirements of different AC induction machines were applied to different applications. Some applications, like fans, just accelerate up to speed and run at that speed all day and don't start and stop many times. Other induction motors are used to start large loads, large torque loads or large inertial loads, such as air compressors or induction motors that start various types of plant machinery, like steel mill rolls or paper rolls or rubber mills or things of that sort. And so to make these motors perform properly for those variety of applications, optimizing of the rotor bars was a necessity, and evolved into four basic types that are called NEMA type A, B, C, and D. And these are different shaped rotor slots. And here's, we've seen this picture of them before, and here's the four types. As you can see, each rotor lamination has quite a bit different. The shapes are quite different. This one here is very strange. It has sort of two bars in one with a connecting strip between them. And there's a lot of versions of this, many versions of deep bar and double barred rotors. These are designed for applications that require high starting torque, which is not possible with a lamination like this. And this is due to a very unique characteristic of induction motors, and that is that with fixed voltage and frequency to instantly start the motor, the starting torque is very low if the rotor bar resistance is low. So if you have a high rotor bar resistance, you can get a very high starting torque. But that condition works against you for the efficiency of the machine up at rated speed. So for high starting torques, you use these kind of rotor bars, and for machines that don't require high starting loads, you use these types. So which ones are necessary for inverter duty? And are any of them useful for inverter duty? So that's what we're here to talk about. The rotor itself consists of a core, a round core made of steel laminations that are punched out of the stator hole, as we've said before, and stacked together on the shaft to form what's known as the rotor core. Then this core has those slots in it we saw in the previous picture, and those slots are filled with some kind of a conductive material, such as aluminum or copper. And to become the secondary of the rotating transformer, which is what the induction motor consists of, the bars, the slots contain conductors which they call rotor bars, and they are connected to a end ring or a big washer at each end of similar material, or if not the same material. And so that's why it's called a cage. It's called a cage, like a cage with a squirrel inside of it. These are easily manufactured by die casting in aluminum, and that's been very popular and cheap, low cost over the last 100 years. But this cage only has one turn in it, no matter how many turns there are in the the stator phase. The stator phase changes its number of turns based on the voltage of the supply. For example, if a motor has 10 turns per coil for a 100-volt operation, the same motor, to get the same power, torque, and efficiency, would need twice as many turns per coil, or 20 turns per coil, for a 210 or 220 volt motor. A 48 volt motor would need half as many turns per coil. But all these motors still use one turn in the rotor. The aluminum die casting, the quality of aluminum die casting is very important. Here it shows a cross section of a fairly large machine, in which case we have the stator lam punchings are stacked on the shaft. There's actually a key shown in here, but they're stacked in groups. This is a stack of lambs, and this is a stack of lambs. And these lines here, this here represent a passageway for cooling. And the bars come down here and attach to this end ring. And many times, as we'll see on the next slide, there's fan blades cast right in the end ring. In this case, this is a larger machine, and there's no fans blades cast to it. They add an extra fan to circulate air past this thing and on the inside of the stator end turns. Here's what I was referring to. Here's a small single-phase rotor with a die casting in it. You can see the die casting goes down the slot. One thing that's very important here is the accurate stacking of the punchings, so that I have a uniform cross-section for that bar conductor. Remember, I showed in an earlier tutorial a very poorly stacked one, such that they were so misaligned. The laminations were so misaligned that in some of the cases along this bar, the lamination completely closed off the passage, so there was either high resistance or open down the bar. So you have these bars cast in the end rings, and these are the fan blades cast onto it. And you notice some of them here are bent. That might be intentional. That might be used for balance. My experience has been you clip off some of this for balance, but maybe they bend them to move. I'm not sure that's effective for balance. They could have just dropped this, or mishandling could have bent them. I'm not sure. But in any case, here's a cartoon representation of a typical squirrel cage, and the forces on the bars that produce the torque, plus the centrifugal forces, or the well, not centrifugal forces, the tangential forces. When this thing accelerates, there's the end ring, the mass of the end rings is accelerated or moved by the bars themselves that stick into it. So there's a shear stress on the bars there, and if the starting forces are real high, then these constant tangential shear or end ring forces on the shear stress cause high shear stresses on the bars, which will cause them to work harden and to eventually crack and fail. So the stresses on these have been of great concern for motors that are grid powered, and we'll study more about that later. Here's a picture of some pictures of a die-cast aluminum. You can see the beautiful stacking here, skewed stack, and beautiful casting job here, been machined. And here's the fan blades, and here's an example, some die-cast copper rotors with quite wide slot openings, and the copper's cast right to the surface of the OD, which is a good thing. You want the bar conductors as close to the OD as possible for an inverter-driven motor to reduce the leakage reactance in the rotor. And this keeps the power factor up, so that's a good thing. So that's a beautiful example. The Siemens has given us some die casting details that are important. Here's a list of them. You can study those, and it's very important to control the shot temperature, the clamping pressure of the cores themselves, and it's important to put the shaft inside before it cools, so that you don't have to reheat it later and cause more stresses on the assembly. And here's a list of the recommended die casting temperatures used, pressures and temperatures used for die casting aluminum and copper. You can see that these are the melt temperatures required to get a good casting, 1200 degrees and 2000 degrees. So the copper's tougher. It's going to require different die materials because of that. Then the shot pressure, that's the pressure, hydraulic pressure used to shoot the molten aluminum into the cavity. And then while you're doing that, you have to clamp the lambs together at a higher pressure than the shot pressure. So you can see there's quite a big difference for the copper. That's another problem, I assume. That's very important to have this high clamping pressure, because you don't want the shot pressure to kind of open the die and force the casting material down between the laminations. That's a disaster. Now, not all machines are cast. As I indicated before, there's a size limitation on casting. I think it's 30 inches in diameter and 50 inches long is about the biggest they can die cast today, without unreasonable costs for the dies and so on. So without being able to cast them, you have to fabricate them. And here's a nice large picture of a big machine, a big rotor, that shows all the elements that you're faced with when you're fabricating a rotor, a caged rotor. And it doesn't matter whether it's aluminum or copper. This one happens to be copper. But what we see are these packets or stacks of lambs that have been stacked up on the shaft with the ventilating passageways through them, through spaced laminations that are fabricated and used to evenly space those. And then those are ventilating ducts for cooling, and the bars extend through those vent ducts, so they have direct exposure to the gas or air that's blown through there, pumped through there for cooling. And you'll notice that here's the end rings, and the bars extend past the core to be attached to the end rings. Now, they don't usually extend them past for aluminum, but they do for copper. And this acts as a fan, actually. See, when this spins, these extended blades here, they're there to eliminate bending, and due to thermal expansion and tangential shear stresses due to carrying the mass of the end ring, and you allow these to be in bending instead of shear. And so it takes longer for them to work harden and crack and fail. That's why they extend the pass like that, plus past the bore like that. But this gives you the added benefit of a centrifugal fan in there to cool the rotor and the stator end turns that are right above this as well. So let's see, I guess that's all we need to say about that guy. Now let's look at an example of two fabricated caged rotors, and they're identical. The core links are the same. I'm not sure, maybe the core links aren't the same, but I guess they are. But at least they have stacks of lambs with the ventilation passageways through it, just like we talked about. Here there's aluminum bars down there that have been welded somehow to this end ring, and there's fan blades in there. Those are probably all welded and fabricated as well, and then it's welded to this plate here that supports it. I suppose they put bolts in here or something like that for balance, I presume. Those are probably balancing. You see there's some mass of some sort that was put into those holes there. That's probably for balancing. And so you still have the centrifugal fan effect, but apparently you don't have the stress problems on the bars, so you don't need to extend the aluminum past the rotor. I'm saying apparently because I don't have first-hand experience with the hows or whys of that. In the case of the copper one, it's like the other ones we saw, that the bars extend past the core and they're attached to a thick end ring. And I'm not sure what these grooves are for. I don't really know what those are for. But there's certainly a centrifugal fan effect in coolness as well. Now the bars themselves, as they go down into the slots, if you're fabricating, you have to have clearance. So you'll notice here that there's clearance around the bar, and that'll allow the bars to vibrate. And the bar vibration, here's the bar vibration frequency, and the high AC rotor currents during starting of grid-powered motors at least cause bar vibrating forces that will cause them to fail eventually. But so what you do about that, typically they swage them in. They use a heavy tool and a hydraulic press, and they apply it here, and they mash this down, which forces it at the bottom of the slot and spreads it out here, tightening it up in the bar. Now that's a laborious, one bar at a time, horrendous thing to do, but it must be done in large machines. The high-speed machine tool spindle people, they don't do this. They fill this full of a brazing paste, a silver brazing paste, and when they're brazing the bars to the end ring, they fill the slots in the rotor with the same paste. So they stick this in an oven at 1500 degrees for an hour, and it silver solders the bars in place to the core. It works very well. All high-speed grinders and a lot of machine tool spindles use this technique. But I have to think that I've tried a couple of induction machines where I've used Loctite products to you warm this thing up so you get good suction and capillary action from the temperature differential, and you apply Loctite, the bolt type, the high temperature Loctite. I forget the number that you use for holding fasteners, and that just sucks its way around and wicks in here, and I've found that works very well. But I have to confess that I haven't life tested this sufficiently to say that that's a long-term viable thing. But I've discussed this with the Loctite people, and I plan to do more investigation with that, and I encourage you to do it as well. I think it's an excellent low-cost way to retain bars in these machines without having to swage. The shape of the bars, as we're going to study more, is very important, and the teardrop shaped or the trapezoid or the tapered side bars seem to be the most successful for inverter duty. They can be extruded, cast, or machined. The prototypes I've machined them. They cost a lot of money, so eventually you got to extrude them, because copper extrusions are pretty reasonable. Parallel sided bars are lower in cost to make, but you wind up with tapered rotor teeth, and this will cause the extra zigzag losses in the machine due to inner bar resistances, which we'll talk about in the next tutorial. But in either case, the bars have to be restrained to prevent any motion. The end rings have to be attached correctly, as we've talked about. The choices are high temperature oven brazing, induction soldering, welding by laser, plasma, TIG or MIG, and most recently stir-welding. I love the stir-welding techniques, and this is what stir-welding looks like. Use a special bit, looks like a kind of a fancy end mill, and it's got a probe that protrudes down the center of the bit, and this has this big shoulder on it, and the R&D and development work is all centered around what this probe looks like, its shape and all that sort of thing. It essentially, what it does, it uses heat and a little cutting action and friction to drill in right into the center of the joint of the two pieces you want to fuse together. And that heat causes whatever this material is to melt, to come liquid. And so then you keep it hot in this whole area by the friction pressure on this face of the tool, right here. So this is hot here, but this is molten. So you keep moving. You apply a lot of vertical pressure, and you apply pressure in this direction, and you feed this all the way to the end, and this is centered right in the union joint. And so this cools and chills behind it, and you get a beautiful welded or alloyed together the two pieces. And this can be applied to a lot of different configurations. Here's a bunch of joints that are made that way. You can study these butt joints, lap joints, you know, parallel joints, all kinds of joints could be done the same way. Well, now here's an example of how that technology has been applied. General Motors applied this to the welding of end rings to copper bars. Here's your bars, here's your laminations. We're looking at the end. There's your end ring, there's your end ring. And so here's a tool that melts and fuses this together, and uses a CNC machine to rotate the rotor so that the tool is right over the center of the bars, and you go around in a circle and you get a beautiful welded joint. Hitachi also has patents on this. I wouldn't be concerned about the patents. Study them and make sure you don't violate them, but I think their patent is just on the tool shape or the angle of the tool. You could try this from the OD, you could try it on a little angle. I think there's all, you have a process of welding, a welding process. It seems strange to me that the patent office would allow an application patent. You know, I mean, this is like I've got a welding. I buy a welding torch, but I can't use it to weld my frame of my machine together because somebody's got a patent on that. You can't weld machines together, or you can't. I can't stir weld rotors for induction motors together, but I could stir weld wings on airplanes together. I mean, that to me that doesn't make sense. So I suppose there's ways to get around those patents, but I'm not sure. I'll leave that up to you. Here's an example of a big fabricated copper. This has been brazed, induction brazed, right? Only on the face. Some of them will cut a groove in there, a tree pan in there to improve the brazing process, but this is just butt brazed. I think that's dangerous, but this is a very popular motor that's used for rapid transit traction by, let's see, these are used by Bombardier in Montreal, and there's a company in Montreal that makes lots of these every year. This is a motor that I built for a high-speed application, 12,000 RPM, and see, in the length of the machine, the centrifugal force of the bars would cause them to bow out. So I had there's a thick end ring on here with milled grooves, the shape of the teardrop extruded bars. These bars were not extruded, they were milled, but they could be extruded. So they fit down in the slots, and we just pasted this whole thing full of this silver solder brazing paste and put this whole thing in an oven for an hour and a half and brazed the whole thing together. All the bars are brazed in the slots so they can't move, and they're also brazed to the end rings, and this was very successful high-performance induction machine. This is an example of a copper die-cast induction motor. You can see the die casting there, and it's got a slight skew on it. You see the copper going down the bars. Now, as I mentioned before, on large machines, the forces on the bars are horrendous. This is a Alstom, made by Alstom in France or someplace in Europe. A great big induction machine, probably used for a wind turbine. I'm not sure what it's used for, but Dr. Penrose, he talks about the forces on the rotor and has written some papers on that and the effects of it for bar breakage, and in his papers he shows this diagram of what the electromagnetic tangential forces on the bars are as during starting of a machine from the grid. And in calculating those, you create the casting as one solid mass, and there's centrifugal forces that are on the bars as well as inertia forces from what's hanging on the ends. This is a nice chart that's provided by the Society to promote the use of copper rotors instead of aluminum, and this is actual test data from these different horsepower motors. Here's the frequencies. This work was done in France, so most of them are at 50 hertz. There's a few 60s here. And then you've got the efficiency comparison of the machines as a function of horsepower of aluminum rotor versus a copper rotor. All they do is replace the aluminum rotor with a copper rotor. And look at in a 1.5 horsepower, the efficiency improvement is 7.1 points of efficiency. Of course, the higher you go, the less significant it is, but it's still significant. A 1.6% efficiency of 25 horsepower is a lot of power savings over the year. So, and you've reduced the rotor losses substantially, so this allows you to rate the motor actually a little higher, as a matter of fact. Here's some more comparison data provided by, there's a reference down here, motor driven systems in September 58, 2005 at this association, EEMDOS 2005 in Heidelberg. And this is a comparison presented of the difference in current and power factor. You see the improvement in power factor from aluminum, copper. Not all cases here, the power factor went down. In these cases it went up. I'm not sure why that is, but there's probably some good reasons for that. Here's an example of a 3/4 kilowatt machine that shows the die-cast copper rotor, and here's the torque speed curve for copper and aluminum, what the difference is. The aluminum has high starting torque, but you don't care about that with an inverter drive, because you take care of this. The starting torque is low with the copper because of its low resistance. It's low because it has a it's low because the resistance is lower, but that doesn't really matter when you drive this motor with an inverter. You want the lowest resistance rotor possible. We take care of this fixed frequency. The reason it's lower is because of the fixed frequency, and when the motor is first started, it sees this huge starting current, and it sees this huge slip. And so that's why the starting torque is so low. But with an inverter, we control the frequency and the voltage so that this problem is mitigated. It goes away. It's not there. Don't have to worry about it. So the old rotor bar configurations for grid powered machines don't apply. And we're going to study more about that in the next lecture. But here's an example of a large induction motor with copper. And as you can see, you clamp your sections of laminations between the vent spacings, and you use through bolts here to clamp these together, because you've spaced the end ring considerably past the end of the core. So I can't clamp it out here. I have to clamp it in here. And since these laminations would be free, I make this clamp plate have fingers on it that clamp right on the teeth to keep the teeth from moving or vibrating. And then these tie bolts here and nuts and washers here clamp this up, and then the rotor bar and end rings can be fabricated. Now that contrasts with the same rotor with aluminum, in which case I don't need the clamping. I still have the vents, still have the groups, but this the aluminum end ring is right up against the laminations. And this is either poured, cast, or welded the same. So I believe that concludes this